All right, let's talk a little bit about a more generalized or version of the hypergeometric distribution here, also known as the multivariate hypergeometric distribution. I'm just going to tag along off of the last example we did in the previous video. In a standard deck of 52 cards, you were dealt a hand of 13. Let's find, how about the following? Let's find the probability of being dealt, let's say in the hand of 13, the probability of being dealt, let's say 3 aces and 2 queens. 3 aces and 2 queens. Okay, so this is a little bit more complicated because now what is our success here? Our success is getting 3 aces and 2 queens. All right. So how can we get the desired probability? Well, we are still picking from 52 cards and we're still getting dealt a hand of 13, right? Still 52, choose 13 at the bottom. But we're going to extend sort of our combinations at the top here to include basically the possible successes, right? The count of the number of successes. But we can't do it in one combination. We're going to need to do 2 combinations. So what are our successes? Well, there's 3 aces that you want. And in a standard deck of 52 cards, there are 4 aces. So you need 3 of those. And then we need 2 queens as well. So there's 4 queens in the deck. We need 2 of those. So 4 choose 3 times 4 choose 2. That is like our success probability. And I don't really need to put that in brackets because we can just, it's multiplication. So we'll be fine there. But then you still have that last term of what else do you have? What are your other failures, right? Our failures here, let's see here. There's 52 cards. What else do we have left? Well, the aces were successes and the queens were successes. So we got to get rid of those 8 cards. So from the remaining, what is 52 minus 8? From the remaining 44, we need to choose how many cards? We need a hand of 13. We've already got 5 because we got the 3 aces and 2 queens. So we would need 8 from the other 44. We would need 8 from the other 44. So that would be, we'd have to run through the probabilities there. I guess I can just go ahead and do that here. So what is 4 choose 3? Let's see here. 4 choose 3 is 4. 4 choose 2 is 6. 44 choose 8 is probably pretty large here. 44 choose 8 is a large number. So I'm going to leave that in the calculator. So I'm going to do that times 6 times 4. Well, let me write this down here. Actually, this is 177 2 3 2 6 2 7. So, and there we go. All that divided by 52 choose 13 should be a familiar number if you've done a lot of these card questions. That is a lot of cards, actually. That is getting to be times 10 to the 11th in my calculator. So I need to do this all in my calculator here. So 52 choose 13. All right, so I'm going to do 4 times 6 times 177, 232, 627 equals. And then I'm going to do divided by, and then in parentheses, 52 choose 13, close parentheses. Okay, so then this is about 0.006698 is what I can see on there. Okay, 3 aces and 2 queens. All right, and so you can extend this to any number of different sort of buckets of success that you want, for example, right? So you could say, find the probability of getting, let's say, let's find the probability of getting, well, here, let's just add to this. Let's say 3 aces, 2 queens, and 1, 5. 3 aces, 2 queens, and 1, 5. All right, so how is this going to extend? So we still have 52 choose 13. So 3 aces. So what are our successes here? So out of the aces, there are 4 choose 3 of those. There are queens. There's 4 possible queens. Choose 2 of those. Out of the, let's make this a little more interesting. Let's say 1, 5. Let me make this more interesting. Let's say 1 odd number. 1 odd number. So what's an odd number? That would be a 3, a 5, a 7, or a 9. 1 odd number. A 3, 5, 7, or a 9. 3, 5, 7, or 9. Okay. How about that? Did I make this complicated enough? Let's see. So we're going to need 1 more success here. Now, how many successes does this get to choose from? Well, there's 4 of each of these ranks. There's 4 3s, 4 5s, 4 7s, and 4 9s. So there's 16 possibilities that we could get from. We're going to need to choose 1 of those. So there's our successes. Now, how about our failures? Well, we got a hand of 13, and we've got 3 plus 2 plus 1 cards that are 3 aces, 2 queens, and 1 odd number. So we've already chosen 6. So we would need 7 other cards to be considered from the other set of hands. And what's left over? Well, of the 52, you're not getting any more aces, so subtract 4. You're not getting any more queens, subtract 4. And you're not getting another odd number, so subtract 16. So you're going to choose 7 from the 28. You're going to choose 7 from the 28. Okay? And then so this would be 4, choose 3 is 4 times 6. 16, choose 1 is 6. 28, choose 7, I'm guessing is pretty large. It's not too bad. 28, choose 7 is 1184040. So there we go. So 1,184,040 ways. And then 52, choose 13, yet again, is 52, choose 13. So we can punch this in a calculator. 1,184,040 times 16 times 6 times 4 divided by parentheses. 52, choose 13, close parentheses. And what do we got? Something slightly higher than the previous question. Less likely. 0.000716. 0.000716. We have an extra 0 here. Does that make sense compared to part C? Does this make sense? I would say yes. Why is part D less likely than part C? Well, it's a more specific outcome, right? Part C includes all the possibilities you can get in D and any evens, right? And any evens. So it should be actually drastically more likely to just get 3 aces and 2 queens than it is to require 3 aces, 2 queens, and a single odd number. All right. Good. So we have that. The last thing I want to do in this video is just kind of offer maybe a little bit of an interesting side project for those of you who might be interested, specifically for those of you who like to play poker. And with poker, we're talking about getting a 5-card hand from 52. Okay. And in poker, there's an ordering of hands that you can get. And the highest ranked hand is the winner. And so they go in this order. You've got a royal flush, which is a 10 jack, queen, king, ace of 1 suit. You've got a straight. You've got a straight flush, which is 5 cards in an order, but it's any 5 cards in an order excluding a royal flush. So Straight flush could be like a 2, 3, 4, 5, 6 in the same suit. You could get 4 of a kind. 4 of a kind. You can get a full house. You can get a full house. You can get a flush. You can get a flush. Then a straight is next on the list. There's a straight. Then there's 3 of a kind. 3 of a kind. 2 pairs. 2 different pairs. So like you could get like a 6 and a 6 and maybe a 10 and a 10. And then 1 random 5th card. And a 1 pair. And a 1 pair. And these are the poker hands in order. They're ranked like this because of the probability of getting these in order. A royal flush is the least likely hand to be dealt. It is the least likely to be dealt there, okay? And so something we could think about then is this is very closely related to the hypergeometric distribution. All of these are going to have a total sample size of 52 choose 5. If you want to calculate the probability of getting dealt any one of these hands here, then all you have to do is count the number of ways to get that hand and divide it by 52 choose 5. Okay? And I think you would find that it is very closely related to the hypergeometric distribution with some slight generalities. Okay? So I'll just do one example here for those of you who might be interested in this, and then I'll let it go because this is going above and beyond what we need to really cover in this course. Let's take a full house, for example. Let's take a full house, for example. And let's take a specific full house. Let's take a specific full house, all right? So a full house is essentially a 3 of a kind and a 2 of a kind. So let's take a full house, and let's say you're going to get 3 aces and 2 queens. 3 aces and 2 queens, okay? Well, based on what we know, this is just going to be 4 choose 3, 4 choose 2, over 52 choose 5. Over 52 choose 5, right? And we can compute that probability. That would be some probability, right? Now, this is only, though, for 3 aces and 2 queens, right? So how do you do the general full house? Well, a general full house, what's the probability of getting a full house in general? That would be any combination of a 3 of a kind and 2 of a kind. So you would say 3 of blank and 2 of blank. All right. So what you need to do here is pick a suit here, and you get to pick, or not a suit, but pick a rank here, aces, 5, 2, 3, 4, and you pick a rank here. They have to be different, though. They have to be different. So what do we do? Well, choose. How many different ranks are there? You've got a 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, ace. There's 13 different ranks. So there are 13 of them. There are 13 of them. You've got to choose one of them to go here. You got to choose one of them to go there, right? Then what can you choose for your 2 of a kind? Well, it has to be a different rank. There are 12 left, and you choose one of them to go here. Maybe it's a queen. Maybe it's a king, whatever. So to get a general full house, you would say there are 13 choose 1 possibilities for the rank of my 3 of a kind. Now, to get a 3 of a kind, once I've chosen the rank, let's say it's aces, there are always 4 of them, and I need 3 of those. Then, for the 2 of a kind, I need to choose that rank. There are 12 left over, and I need to pick 2 from the 4 of those. Over 52 choose 5. And that would be the general probability of getting a full house. That would be a general probability of getting a full house, okay? And you can take that sort of strategy for a 4 of a kind, for a 3 of a kind, 2 pairs and things like that, all going to follow in a similar strategy. The straights take on a little bit of a different approach. There's one slight different way you have to think about your straights when it comes to identifying this step. And maybe I'll let you think about that on your own time if you would like to do so. But I just want to mention that all we really need to know to talk about poker odds and understand where all of these numbers and rankings come from is just the hypergeometric distribution, which hopefully now we have some familiarity with.